Welcome to Abstracts, a Microsoft research podcast that puts the spotlight on world-class research. In brief, I'm Amber Tingle. In this series, members of the research community at Microsoft give us a quick snapshot or a podcast abstract of their new and noteworthy papers. Our guest today is Dylan Foster. He is a principal researcher at Microsoft Research and co-author of a paper called Reinforcement Learning Under Latent Dynamics Towards Statistical and Algorithmic Modularity. The work is among the oral presentations at this year's Conference on Neural Information Processing Systems, or NeurIPS, in Vancouver. Dylan, welcome, and thank you for joining us on the podcast.
Thanks for having me.
Let's start with a brief overview of this paper. Tell us about the problem this work addresses and why the research community should know about it.
So this is a kind of a theoretical work on reinforcement learning, or RL. When I say reinforcement learning, broadly speaking, this is talking about the question of how can we design AI agents that are capable of interacting with unknown environments and learning how to solve problems through trial and error. So this is part of some broader agenda we've been doing on kind of theoretical foundations of RL. And the key questions we're looking at here are what are called exploration and sample efficiency. So this just means we're trying to understand what are the algorithm design principles that can allow you to explore an unknown environment and learn as quickly as possible. What we're doing in this paper is we're kind of looking at how can you most efficiently solve reinforcement learning problems where you're faced with very high dimensional observations, but the underlying dynamics of the system you're interacting with are simple. So this is a setting that occurs in a lot of natural reinforcement learning and control problems, especially in the context of say embodied decision making. So if you think about, say, games like Pong, the state of the game, the state of Pong is extremely simple. It's just, what is the position and velocity of the ball and where are the paddles? But what we'd like to be able to do is learn to, control or solve games like this from raw pixels or images, kind of in the same way that a human would, just solve them from vision. So if you look at these types of problems, we call these RL with rich observations or RL with latent dynamics. These are interesting because they kind of require you to explore the system, but they also require, representation learning. You want to be able to use neural nets to learn a mapping from, say, the images you see to the latent state of the system. This is a pretty interesting and non-trivial algorithmic problem. And kind of what we do in this work is we take a first step towards something like a unified understanding for how to solve these sorts of rich observation or latent dynamics RL problems.
So how did you go about developing this theoretical framework?
Yeah, so if you look at these sort of RL problems with latent dynamics, this is something that's actually received a lot of investigation in theory, and a lot of this goes back to kind of early work from our lab from 2016, 2017 or so. There's some really interesting results here, but progress was largely on a case-by-case basis, meaning there are many different ways that you can try to model the latent dynamics of your problem. And each of these somehow leads to a different algorithm, right? So you think very hard about this modeling assumption. You think about what would an optimal algorithm look like, and you end up, writing an entire paper about it. And there's nothing wrong with that per se, but if you want to be able to iterate quickly and kind of try different modeling assumptions and see what works in practice, this is not really tenable. It's just too slow. And so the starting point for this work was to kind of try to take a different and more modular approach. So the idea is, there are many, many different types of sort of systems or modeling assumptions for the dynamics that have been already studied extensively and have entire papers about them for the simpler setting in which you can directly see the state of the system. And so what we wanted to ask here is, is it possible to use these existing results in more of like a modular fashion? Like if someone has already written a paper on how to optimally solve a particular type of MDP or Markov decision process, can we just take their algorithm as is and perhaps plug it into some kind of meta algorithm that can directly kind of combine this with representation learning and use it to solve the corresponding rich observation or latent dynamics RL problem?
What were your major findings? What did you learn during this process?
We started by asking the question sort of exactly in the way that I just posed it, right? Like, can we take existing algorithms and use them to solve rich observation RL problems in a modular fashion? And this turned out to be really tricky. Like, there's a lot of natural algorithms you might try that seem promising at first, but don't exactly work out. And what this kind of led us to, and sort of the first main result in this paper, is actually a negative result. So what we actually showed is most sort of well-studied types of systems, or like MDPs, that have been studied in like the prior literature on RL, even if they're tractable when you're able to directly see the state of the system, they can become statistically intractable once you add sort of high dimensional observations to the picture. And statistically tractable here means the amount of interaction that you need, like the amount of sort of attempts to explore the system that you need in order to learn a good decision-making policy, becomes like very, very large, like much, much larger than the corresponding sort of complexity if you were able to directly see the states of the system. You know, you could look at this and say, I guess we're out of luck. You know, maybe there's just no hope of solving these sorts of problems. But that's perhaps a little too pessimistic. You know, really the way you should interpret this result is just that you need more assumptions. And that's precisely what the sort of second result we have in this paper is. So our second result shows that you can sort of bypass this impossibility result and, you know, achieve truly modular algorithms under a couple different types of additional assumptions.
Dylan, I'd like to know, and I'm sure our audience would too, what this work means when it comes to real world application. What impact will this have on the research community?
Yeah, so maybe I'll answer that with two different points. The first one is a broader point, which is, why is it important to understand this problem of exploration and sample efficiency in reinforcement learning? If you look at the sort of setting we study in this paper, you know, this like RL or decision making with high dimensional observations, on the empirical side, people have made a huge amount of progress on this problem through deep reinforcement learning. This was what kind of led to these amazing breakthroughs in solving games like Atari in the last decade. But if you look at these results, the gains are somehow more coming from the like inductive bias or the like generalization abilities of deep learning, and not necessarily from the specific algorithms. So like current algorithms do not actually explore very deliberately, and so their sample efficiency is very high. Like it's hard to draw a one-to-one comparison, but you can argue they need like far more experience than a human would to solve these sorts of problems. So it's not clear that we're really anywhere near the ceiling of what can be achieved in terms of like how efficiently can you have, you know, an agent learn to solve new problems from trial and error. And I think better algorithms here could potentially be like transformative in a lot of different domains. To get into this specific work, I think there's a couple of important takeaways for researchers. One is that by giving this impossibility result that shows that RL with latent dynamics is impossible without further assumptions, we're kind of narrowing down the search space where other researchers can look for efficient algorithms. The second takeaway is, you know, we are showing that this problem becomes tractable when you make additional assumptions, but I view these more as like a proof of concept. Like we're kind of showing for the first time that it is possible to do something non-trivial. But I think a lot more work and research will be required in order to like, you know, build on this and take this to something that could lead to like practical algorithms.
Well, Dylan Foster, thank you for joining us today to discuss your paper on reinforcement learning under latent dynamics. We certainly appreciate it.
Thanks a lot. Thanks for having me.
And to our listeners, thank you all for tuning in. If you'd like to read Dylan's paper, you may find a link at aka.ms/abstracts. You can also find the paper on arXiv and on the NeurIPS conference website. I'm Amber Tingle from Microsoft Research, and we hope you'll join us next time on Abstracts.